Good afternoon, ladies and gentlemen. Good afternoon. So we are back to our course of fairy tales. This is me again. Usually I give this tale in the end of the semester, but well, for some, owing to some fluctuations, I do it almost right away. I like this tale very much. For me, it's kind of essence of theoretical physics. Very good illustration how theoretical physics can unite and treat on the same footing the systems, physical situations, which are entirely different from the point of view of experimental physics. And it turns out that in quantum mechanics and statistical physics of classical objects, one can proceed by very similar methods and see very many analogies, which are, of course, helpful. And the lecture will be devoted to this. Right, so what I outline step by step is quantum mechanics first, Schrödinger equation, this superposition of that and a live cat. Actually, I find it very tasteless analogy, but everybody uses it. So I will be doing that as well. And I will also outline classical statistical mechanics with more stress on one-dimensional situation. Right. So we outline two extremes, two different experimental situations, and then we will find equivalence between these two situations from theoretical point of view in two ways. One way, you might have heard about this, it's called path integral method. In this case, we will reduce quantum mechanics of a single particle to, in fact, statistical mechanics of some one-dimensional configurations. And then we turn to classical physics, to statistical mechanics, and we will solve the statistical mechanics. And the method with which we solve it would very much resemble Schrödinger equation. And we will see different analogies. In the end of the lecture, we will play with several examples which are known quantum mechanics and which are easy to understand in statistical mechanics, because I don't assume much background in statistical mechanics. Actually, it's a good question. Who of you has taken the course of advanced statistical mechanics or are taking or going to take? If you could put it into chat, it will be very convenient. Well, okay. Lots of you. Very good, very good. So basically, them I will quickly repeat, which you already know. Good. Anyway, it is good course. Include some advanced chapters. I just don't remember whether it was something about specific about one-dimensional statistical mechanics. But anyway, we will learn it quickly. Right. Let us see. This is a brief summary of Schrödinger equation. Of course, you know this. What is that? It's about wave function. A wave function is a vector in abstract Hilbert space, but it's convenient for us to talk about wave function, which depends on single variable x. Right. Eta-base evolution equation. Wave function in kind of future moments of time is obtained from wave function at a given moment of time times Hamiltonian. Hamiltonian is an operator which governs the dynamics of the wave function. We know that there are stationary solutions to this equation, provided the Hamiltonian is stationary. Here there are levels. Here I sketch some potential. And these purple things, purple lines are levels, energy levels in this potential. Right. So today we will talk only about a single continuous variable x, but well, you know that one it can depend on many variables. It can be formulated for many particles. But well, let us concentrate on what we need. Let us concentrate on a Schrödinger equation of a single particle. Then we know the Hamiltonian, kinetic energy, potential energy. Those are operators that can be given in different representations. Let's stick to X representation. Then, well, we replace operator of momentum with a derivative, and that will be Schrödinger equation for a single quantum variable X. This is undoubtedly familiar to you. Good, quantum mechanics. Now let me talk about statistics. In fact, the formulation of statistics does not depend much whether it's a quantum system or classical. And let me explain why it's so, if you don't know yet. We consider a system which can be in a set of states. If it's a simple system like one particle, this set is simple. For many particle system, which is usual in statistical physics, this set of states is very big, but anyway, there is a set of states. All right, and these states have energies, and you know how does it go further? It is assumed that the whole system is in thermal equilibrium, and that very much determines the probability to be in a certain state. It's given by Boltzmann factor. The probability is proportional to this Boltzmann factor. In order to make it proper probability, one has to normalize it. Normalization coefficient, the sum of all Boltzmann factors It's called partition function. And kind of a beauty of statistical mechanics is that you only want to know one function, this partition function, to determine all observables, all averages over a thermal state. Simplest variable is free energy. This is just given by a log of partition function. You know that there's average energy, which is not quite free energy. That's also termed with entropy. How we do average energy? Well, we just differentiate this partition function with respect to inverse temperature. You have taken, most of you have taken the course. Who can explain me why? Why average energy is given by this?
You can just perform the chain rule in the differentiation. So, and that gives you the result that you want. So you take derivative of ln z with respect to z, which gives you the factor 1 over z, multiplied by derivative over z to the inverse temperature, which gives the prefactor of the energies as a sum over all the states n, with the respective probability weighted.
Right. I would try to prove it, this formula from opposite end. First, I would concentrate on average energy. And what is this? It is energy taken with probabilities. Probabilities are Boltzmann factor. I take beta for inverse temperature. Boltzmann factors divided by z. But all of this is a derivative of z with respect to beta. Right? Building it here, we reproduce this formula. Fine. The same goes for all quantities. For instance, there's some variable x, and I want to determine its thermodynamic average. What I do, I add a small term to energy, where this x comes with conjugated force. And the average of x is given by derivative of, again, it is log of partition function with respect to this force. All right. That's don't know how was it, if it was sufficiently stressed in your course, but these pairs, variables and conjugated forces, are very important in thermodynamics and statistical mechanics. Such pairs, for instance, volume, pressure, magnetization, magnetic field. So there's plenty of those pairs. Does it ring the bell? Variable and conjugated force. No? Are you sure that you've taken to thermodynamics? Pressure times volume. So pressure is conjugated force with respect to volume. Volume is conjugated force with respect to pressure. It is similar construction in the Legendre transform, but it's a very much general. So now you recall, Nika. What made you to recall this? Which words kind of runs a bell? Nico. Pressure volume. Okay, pressure volume, it's kind of traditional because initially thermodynamics have been formulated for the gases. And right, it's a traditional example. But all physical values have their conjugated forces. That's what I said. So here I just took a kind of displacement of something, and a mechanical force is conjugated force to displacement. Very good. So let us now understand that what we need is partition function. And that's the beauty of statistical mechanics. And let me turn to a particular example, which I guess you know, at least. I wonder if there was a lecture on the subject, or was it mentioned somehow? Perhaps exercise, presentation. One-dimensional Eisen model. Both pronunciations are good. You've done the analytic solution. Yes, we have seen that. Into the right. Into the, yes, it also, no. I don't think you did exact solution into the, this, it's possible, but I'm not sure that, right, analytic into the, yeah, okay, you recall it. It is used because it just a very minimal model of statistical mechanics. It is ultimately discretized both in the value of variable you look at and in space. So one-dimensional axis is separated by nodes, as you see here. And at each node, there's a variable which can take only two values, which are kind of traditionally called spin directions, plus minus. Good. So what are components of energy? There's magnetic field, and that works on a single node only. That's not enough to make an interesting model, because if I stick to this, I would just have isolated spins. There must be something which provides interaction between spins. So there's also energy per bond. right? It depends on the product of spins. Depending on the sign of J, it either tries to align spins or make them opposite. Fine. So we concentrate on one-dimensional lattice, and the partition function can be written like this, where summation is over all possible configurations of sigma in this infinite, well, in principle, infinite chain. Fine. Some words about Eisen. When he was Eisen, so he lived in Germany. He became a PhD, and he got a PhD project to understand the magnetism in solids. As a matter of fact, he appeared to be not very bright or quick PhD student. So supervisor had to simplify as a project more and more and more till they come to classical spins. That's not quantum mechanics is a problem. And the one-dimensional situation. And then that PhD student was managed to solve this problem. Let's see what I have here. Here it's a realization of Eisen model. In this case, it's a carbon nanotube, and within this nanotube, somebody put molecules. And these molecules, C70, can be in, it's like a elliptic, and it can be in two configurations with respect to nanotube, either parallel or perpendicular to nanotube axis. And there is interaction between these molecules which enables aligning. So it's is either this configuration or opposite configuration. Fine. Control question. What is magnetic field in this problem? Yeah. Here in Eisen model, original Eisen model, this is something which distinguishes local configurations, one node configurations. For our models, there are two configurations along the axis and perpendicular to the axis. They have, as you can imagine, a little bit different energy. In fact, yeah, it's a force from the nanotube one can say. But one could just say they have a little bit different energy, and this energy goes to this effective magnetic field. Fine. So I think we recall Eisen model. Energy on a single node, energy on a bond between two different nodes. Now I wanna get to real stuff. Oh no, sorry. I still have to say a lot about thermodynamics. I wanna talk, not that I want to derive, I want to motivate, as you see, Landau Hamiltonian. It's a bit of slang, perhaps Hamiltonian, it's not a good word for that, but it's frequently called Hamiltonian. And this is to describe second order phase transitions. Who looking at this form recalls this immediately. I don't feel the majority. Yeah, although yeah, if you tried randomization that you have them, it means that you have to deal with a sort of Landau Hamiltonian closer to critical point. Fine. So let me whatever derive or motivate it. Yes. So we consider now variables which are not discreteless in Eisen model, but continuous. So there is a magnetization. I will call it X, but it's not coordinate. Coordinate is Y. Right. These variables can be made continuous if I start from discrete variable. In this case, I just take many nodes where discrete variables are defined and treat it as a single node, right? This is what is commonly called coarse graining in statistical physics. Does this ring the bell? Coarse graining. Anyway, in short, for one node of Eisen model, you have two values of a variable. Let's take 10 nodes as a single node. We take 10 nodes as a single node, and then this variable can take 10 possible values. Let's take more nodes. It will become will have even more values. So from discrete variable, it will become continuous. The same one can do in the space, assuming that the variations of this variable happen at space scale larger than the distance between the nodes. Then one can treat y as continuous variable. So we do. Let us now make some free energy, which depends on the local magnetization as a function. Okay, what we can have is a local term. Right, I take 10 nodes in a as a single node, right? In each node, I have plus, minus, plus, minus, plus, minus. I would like to understand the full magnetization of the node. That can take all values from minus 10 to plus 10. So if one increases number of nodes, one can have this magnetization to become more and more continuous. Right. So first of all, there is a term which is local in a variable y, which can be quite complex, but this is not enough for a reasonable model. Let me stress this. I don't know whether you talk about gradient terms, but one has to make this magnetization smooth. One has to pay energy phi for in homogeneity of this variable, right? If you don't pay this, there will be gigantic fluctuations of magnetization in neighboring points, which would not correlate. And the concept of continuous variable won't work. So one has to add a gradient to what I put here is a squared of the derivative of magnetization with respect to y. Simplest form of the gradient term. Fine, that defines rather generic one-dimensional statistical model. And now let's get to Landau Hamiltonian. Let's consider second order phase transition. This is a specific form of these functions, which works well to describe second order phase transition, critical point of it. Good. So it's Landau Hamiltonian. We take this U and expand it till second and fourth term in X. We assume that this is even function of X, no odd terms, which implies symmetry. Good. So what is so special about this form? Depending on the sign of t, minimum of this function is either single one and symmetric, precisely at symmetry at the symmetry plane x equals 0, or it could be two equivalent minima, right? So this is common model for second order transition, which is associated with symmetry breaking. So at positive t, we have symmetric solution. At negative t, symmetry is broken. So it either goes to the left well or right well. So on. Does this correspond to your previous knowledge? Have we heard something about this? Do you understand what I'm talking about? Right. Gradient terms are very important. If you start randomization, that they blow up and they could make two very complex scenarios in 2 dimensions, 3 dimensions. You should have heard about this. A critical point is very complex in these dimensions. Fine. Let us see. Now I'm, as a promise, I will prove equivalence of quantum mechanics and statistical mechanics, and I will do it in 2 ways. Let us see. I'm doing with respect to time. Oh, that's fine. All right, so I will go for 10 more minutes, then we'll have a break. And let us see. So, quantum mechanics. Quantum mechanics of a single particle. I took a single particle Hamiltonian. And I would like to treat it thermodynamically. I would like to compute partition function of this particle. So this is what I have to compute. Does it look familiar? Yeah. This is trace of an operator, a trace of operator exponent. Look, if we knew eigenvalues of this Hamiltonian, that will be a piece of cake. But suppose we don't know, we cannot know these eigenvalues. So how we can proceed? The goal is to compute the trace of this operator exponent. And we proceed eventually with very, very counterintuitive method. I thought for a long time trying to find a good analogy in order to motivate you. And I couldn't find before I saw how sushi is made. So everybody knows what sushi is, and originally you don't make these small things. Originally, you just got a very long, thick roll of sushi, and that has to be sliced with very sharp knife before you can eat it. With all due respect, one cannot swallow this roll of sushi. But if you slice it, you can easily deal with a single slice. That's what we are going to do now. Right. I need to talk about imaginary time. And it's about making this exponent. So let us, well, we have this inverse temperature. And this is a parameter in exponent. A parameter which can, for instance, grow. Let me assume that it grows from 0 to this value. And let me define a coordinate, which is called imaginary time. We will see in the end of this page why it is called so. Right. And now I would like to do slicing. So instead of this sushi roll, I would separate this imaginary time axis into small steps, slides with a thickness delta t. So I can represent this exponent as a product of all slices. Okay. Now let me introduce a slice operator. It's an exponent of this operator, and it can be associated with a function which depends on two variables. Is this point clear to everybody? Is it known to you that any operator can be represented as a function of two variables? The width of the piece, be careful, is not x minus x prime. The width of the piece is delta t. X is a variable in which a particle can propagate. Or in other words, X is coordinate and T is time, imaginary time. Right. Let us understand how this operator works on a wave function which depends on X. Right, suppose we have some function before the slice and we apply the slice. So we kind of transfer this wave function to next node. Then we kind of have a discrete Schrödinger equation which describes evolution of this function in this imaginary time. Fine. Now let us take the limit of very thin slices. Then instead of this, one should take a derivative of psi with respect to imaginary time. And the Hamiltonian, exponent of the Hamiltonian can be expanded as exponent so that zeroth term, which is 1, and a small term proportional to delta t. We combine all that, we got the equation. Let me concentrate on it. Which looks very awfully familiar. It is Schrödinger equation. The only point that it misses traditional imaginary unit here. That's why this variable which I have introduced is called imaginary time. Good. So now we want to find a way to execute this multiplication. We kind of figured out more or less what is there with a single slice. One can expand it like this. Now we want to multiply many of them. Let us see. Operator multiplication is extra integration that we have already, we just discussed. Any operator is a matrix. Matrix is a function of two variables. To do matrix multiplication, one integrates over this variable. So it's a formula of matrix multiplication. Very good. So in order to represent multiplication, this matrix multiplication, we have to introduce integration variables at each slice. Plenty of those. Since slices are thin, there's plenty of integration variables. And we integrate it over all possible values. That's how we represent multiplication of these operators. Let us see. I guess you're rather kind of responsive bunch of students. That's meant to be complement. Then who can tell me what is this? What does this term responsible for? What is this term responsible for? As you see, the mere first variable and the last variable of integration are eventually melted together. Why is it so? No. Okay. Look here. Yes, right. This is taking the trace. If I take the trace, and this is a matrix function of two variables, I need to put these two variables to be the same. Very good. So trace assumes that the value of this x at the initial and final point are the same. Fine. Let me come back. So this is for trace, and I multiply all these things. Then, in order to proceed, I want to use approximate commutation of tiny slices. Right? Basically, Hamiltonian is made from two non-commuting operators, one for kinetic energy, another one for potential energy. And it's time to make an 8-minute break. So I would right. So let me start with the second half of the lecture. We are here. We understand that there's approximate commutation for tiny slices. So the exponent of the sum is the product of two exponents. Usually it does not hold for operators, but if delta t is small, this commutation holds. Let us see what we have. We can separate the slice operator onto two parts. A first part is responsible for kinetic energy. Second part is responsible for potential energy. Potential energy part, we write it in X representation. It's very simple. It's just multiplication with this factor, right? And it depends on a single variable corresponding to a node in our statistical models. The kinetic energy term depends on two variables, two neighboring variables. How to evaluate this? It is diagonal in momentum representation. So I have to write it diagonal momentum representation and go from momentum representation to X representation. So that's how these exponents appear. Good, but that I can plainly compute. I can compute this. It's a so-called Gaussian integral. And the answer is as follows. I also put a factor. I complete directly, but I don't care about factors since I compute this z partition function. It will give me just a constant in the log of this function. Don't care much about this. So I concentrate on this. What I see, this is indeed a Gaussian function depending on difference of x and x prime. So since it's probability, it wants to make x and x prime close to each other. All right, very good. So let's combine this. We almost there. That's discrete version of what we have. So I collected all potential energy terms and kinetic energy terms. Now, crucial assumption. Now I assume that this x is a smooth function of imaginary time. In this case, I can go to continuous limit. I can replace the discrete values by derivative of x with respect to tau. Okay. I do this, and this integral, which was inversely proportional to tau, becomes directly proportional to tau. So now I can write all these terms as a single exponent. What stays in this exponent is the integration over imaginary time. What do I have to integrate? I have to integrate the potential energy and the kinetic energy, if you wish. Over imaginary time. So for each configuration of x of tau, I define statistical weight. And I have to sum up over all possible configurations. So that's precisely as a model we have introduced before when we motivate Landau Hamiltonian. This is gradient term. Now I treat tau as a coordinate. This is gradient term, and this is local term. Right? So now we have reduced quantum problem to classical one. We understood that computation of partition function in this case is reduced to solving a one-dimensional classical model. We sum up over configurations of classical one-dimensional field variable x, which depends on coordinate tau. All right. This statistical model is actually defined on a finite length. This length is proportional to inverse temperature. And also of intertrace, these configurations are periodic. Now we can come to periodic boundary conditions. But those arise from the fact that we take trace in the very beginning. Fine. We prove the equivalence in one direction, from from quantum mechanics to classical mechanics, introducing path integral. So this configuration is also called path. Okay, let's go further and let us move from classical mechanics to quantum one. And I take rather general model. I would like to make it a little bit more complex than Eisen model. You will see why. So what is this general model? There's still same nodes as in Eisen model, but in each mode, I define variable x. X, it stands for magnetization everywhere. It can be discrete or continuous, doesn't matter. But there is a variable defined in each node. Very good. Then I define energy per node, like I did for Eisen model, for instance. But this is a function of this variable. This corresponds to Boltzmann weight W2. And energy per bond. That corresponds to weight V1. If you look carefully, I kind of took the notations from a very different problem. This is not my negligence. Look at it, you recognize that the problems are very similar indeed. Why is it true? Because let me now write partition function for thermodynamics of the system. I need to take this weight at all bounds and all nodes, bound nodes, so on. And I have to sum up all configurations on all nodes. So this is my expression of partition function, which is very similar to what we have seen for quantum mechanics. So inspired, let us try to do some quantum mechanics and let us understand what will happen if I have a wave function which is defined on a node, right? On the next node, to define it on the next node, I would have to integrate over one coordinate. That's how this wave function is transformed. It's called transform matrix. Right, so now I want to do the following. Again, using analogy with Schrödinger equation, I would like to find determine eigenvalues of this equation. So I can find the basis of eigenfunctions, which would under this transformation would just retain their shape. They just multiplied by the eigenvalue. All right. I have found this basis. and then there is very little to do more, because partition function is given by these eigenvalues. Partition function is determined from eigenvalues of the transfer matrix. I bet, although I'm not 100% sure, but my bet is that it was the way you have solved one-dimensional Eisen model in your class. Somebody recall this? Indeed. Good. That runs a bell. Very good. So partition function is given by the eigenvalues, and let us see. One could, for instance, do it. I have not specified boundary conditions yet. That would be for periodic boundary conditions, for the system which encompasses n nodes. And in principle, I have some overall eigenvalues. But if I got to the limit of infinite system, to the limit of n to infinity, then owing to this number being big, eigenvalues cannot compete with each other. And the answer is given just by the highest eigenvalue of W. Good. So this is transfer matrix method. Let us compare it with quantum mechanics. Right. For quantum mechanics, at finite temperature, we also need to take into account all eigenvalues of this Hamiltonian, all this EK. But in the limit of low temperature, we just happy with the lowest energy, highest eigenvalue. Right, so it gives us the following association. The length, in fact, corresponds to inverse temperature. Right. That's one thing to know, but we know that already. So we have found that, yeah, at finite temperatures, the statistical mechanics we have to consider for quantum system is defined on a finite length. Right, and we also can make continuous limit. It doesn't make sense to do it in the Eisen model, but we can make it if x is continuous function of I, if I is continuous coordinate. Then again, we can deal with these weight factors in this way. So this is gradient, reintroduction of gradient term again. And this is what we have. So we have indeed full analogy between quantum mechanics and quantum mechanics. Between quantum mechanics and statistical mechanics in one dimension. That's a full analogy. Let me tell you something. I'm not sure. It's just a concrete example of Eisen model. Let me tell you something before I forgot. It's also rather important. We have found association between 1D statistical and zero-dimensional quantum mechanics. If you, for instance, consider two-dimensional statistical models, we can have quantum mechanics of objects which are extended in one dimension, not a particle, but say a string. And so it's an example of quantum field already. And at any dimension n+1 classical mechanics corresponds to n quantum mechanics. One can say that quantum mechanics just adds single variable, this imaginary time, and then the problems become equivalent. Fine. So let me tell you to what you already know. Let me talk about Eisen model. Right. So how to solve this Eisen model external field? It is convenient to symmetrize eigenvalue equation so that the corresponding operator is eventually self-conjugated. So I transformed wave function a bit. I divided by square root of W. Right. So then we can compute it for Eisen. There are two values of spin, and the corresponding weights are just 2x2 matrices. So we've got eigenvalue equation. This is obtained by multiplication of these two factors. We find eigenvalues. We can also find eigenfunctions. Usually it's not needed, but suppose we find eigenfunctions. And now I want to continue this analogy with quantum mechanics. And I would like to tell you that eigenfunctions are also useful. And the expressions where they are useful also look pretty quantum mechanical. Right. Let us ask a question. What would be the average of some variable which is defined at one node? This variable should depend on original variable x. Good. Then I do this machinery of transfer matrix, and that's what I find for the average of this value. Phi naught being the eigenvalue, the eigenfunction corresponding to the highest eigenvalue. So it looks like a wave function of ground state in quantum mechanics. And you see, you recognize the formula for quantum mechanical average. Although we're still talking about classical values. Let us look at the correlations. Let us define this function into two nodes separated by some distance by n bounds. With the same machinery of transfer matrices, we can prove the following equation. How can I interpret it quantum mechanically? Okay, nodes, it's a bit like time. And here in one of the nodes, I go from ground state to some excited state. And this is one matrix element excitation. So now I'm in excited state, okay. And what comes here, it's just energy factor, which I have to pay for this, like an exponent of time proportional to time. N is a time interval now. Right, then I have to come back to ground state. So I have a square root of matrix element and propagation exponent between the nodes. Right, in this way one can find correlation lengths in statistical physics. Just looking at asymptotics of these correlators, it involves next to highest eigenvalue. Now we can define, for instance, correlation lengths for Eisen model. We know both eigenvalues. But this is a kind of energy difference to first excited state. Good. So quantum mechanical analogy works even further, not only for a full partition function, but also for the averages which I have mentioned. Right. So let us see what I wanted to talk about now. Yeah, Eisen model. We can apply this reason to one-dimensional model. We can look at correlations of magnetization. And yeah, I guess the formula contains single exponent, which defines correlation length in terms of the node, which is given by this expression. And there are two limits to look at. First of all, it's a limit of low temperatures and no magnetic field. Remember the physics of Eisen model. So there's no preferential direction for magnetizations. So in fact, the system is separated onto domains. Spins want to be aligned. These domains are just of the order of this correlation length. So if there's no magnetic field, the size of the domain increases with temperature going down. This is nature. Let us consider low temperatures, but finite magnetic fields. Then correlation length is restricted by magnetic field. Why is it so? Because in that case, the domains are not of the same size. It wants to be in energy preferential domain, and domains are of opposite size, of opposite direction of magnetization are thin, and correlation length is given by this length of thinner domains. Fine. We understood these correlations. We will use it when we talk about qubits. So let's see how I'm doing in time. Or eventually pretty good. Somehow fairy tales in Zoom go faster. I cannot say about other courses. So let me talk about qubit physics I have enough time. I can do it rather slowly and in more detail. So if we describe quantum system, make some steps to reduce it to a single qubit, very simplest quantum mechanical system. And then we consider statistical representation of the same system, the same situation. And we'll try to find analogies between quantum mechanics and statistical physics in this particular example. Fine. Let me start with a two-well potential. Quantum two-well potential, which can house a particle. I choose it in this way. What does it mean? First term describes two wells which are at the same energy level, namely at energy 0. So it goes 0 if x is plus minus 1. In addition to that, it's convenient for me to tune a bit the values of this minima. So what I did, I added a small, epsilon is much smaller than mu, a small term, which makes these wells unequal. Right. I want to assume sufficiently strong barrier to have very little tunneling between the wells. Under this condition, wave function in each well somehow localized in either this or this well. The overlap between these wave functions is exponentially small. That's what I have here. So as we know from quantum mechanics, there's quantum tunneling through this barrier, and that mixes levels on the left and on the right. So delta here is tunneling amplitude in energy units. Besides, it has oscillator spectrum around the well, but yeah, I don't want to talk about this at the moment. Here, with this, we can restrict ourselves to ground state of the system, going to energies which are smaller than this omega naught. And there we find only two levels. So this is realization of a qubit tunneling between two wells. So this quantum mechanics of the system is described by two by two matrix. That term which makes wells unequal comes as a diagonal element of the matrix, while tunneling, it mixes states on the left and on the right. So this is non-diagonal matrix element. Fine, we recall this. We have refreshed qubit at advanced quantum mechanics. Fine, what we know about qubits, the energies are given by this expression. So if I plot these energies as functions of epsilon, I would have something like level crossing. So green and red are energies in the left and the right valve. This crossing is avoided because the states are mixed by non-diagonal matrix element, and eventual spectrum is given by hyperpolar. Right. If epsilon 0, if the levels are precisely the same, the resulting wave function, eigenfunctions are equal weight superpositions. So the particle is delocalized in both valves. If epsilon is big, then the wave functions are localized in either upper valve or in the lower valve. All right, that was about qubit. Yet another refression of qubit which you got from me. Let us now try to establish a statistical physics model. So we translate it to 1D, and let me first make it on a formal level, right? So that has kinetic energy, potential energy, and potential energy is, kinetic energy is transferred into gradient term. And potential, something bad with my internet connection, strange. Do you hear me?
Yes.
Very good. And there are local terms of potential energy. Very good. So let us understand it as a statistical mechanics example. First of all, I'm gonna see that the system wants to be in minimum of this potential. So there are two configurations. Let's call X magnetization, two degenerate magnetizations, even for continuous variable. They correspond to the valves, the quantum valves, left and right. For one-dimensional systems, we always have domains. Perhaps it's good to remind you that in one-dimensional systems, we would never have completely ordered state. There's no phase transition in one-dimensional Eisen model, in contrast to 2 dimensions and 3 dimensions, where at a certain moment all spin becomes kind of all spins become aligned. In one-dimensional systems, there are always domains, right? And what is this? What are these domains? Closest analogy is quantum tunneling between these two wells. One can think it's kind of far-fetched analogy, something kind of jumps between two levels. Why does it have to be quantum tunneling? But it is very predictable, this analogy. First of all, thickness of the domain wall is of the order of oscillating frequency. And if you consider tunneling, we also understand that it happens at time scale of going through this potential, at time scale of oscillation frequency. Right. As far as domain walls are concerned, domain wall costs finite energy. And at lower temperatures, this energy the corresponding Boltzmann weight becomes exponentially small. And this corresponds to exponential smallness of quantum tunneling amplitude. Right? So that was without symmetry breaking, external symmetry breaking, without this epsilon. Let's introduce this epsilon. That would work like magnetic field. Some direction of magnetization has become preferential. Then we can compute the free energy of the system. How? Just taking the formula which we have derived for the qubits. Right? So there is a competition between this term describing magnetic field and entropy of domain walls, energies associated, weight associated with domain walls. Right? We differentiate it with respect to epsilon to get magnetization. There is a formula for magnetization derived from the energy levels of a qubit. One can define correlation lengths also, and one can reproduce two limits of correlation lengths, which we got from Eisen model. So either it's domain length of the domain or the length of the smallest domain, the length of domain in without magnetic field, where all domains are the same, or the length of the smallest domain. Good. I guess I'm done. Let's see. I'm still ahead of time. Oh, 20 to 10 minutes ahead of time. So we have quite some time. No, not 20 minutes, 10 minutes ahead of time, right? So we have plenty of time for questions. Thank you for attending. Yes, Sasha, epsilon corresponds to the length of the smallest domain. Sorry,
And I was wondering why in the picture in the top right, epsilon is 0 then.
If epsilon is 0, all domains are of the same length. Yeah. So you don't have to pay energy fine for the domain. Here you have to. So here you have to pay energy to have opposite domain. So the length is defined by this energy fine.
And could you perhaps repeat how quantum tunneling corresponds to the domain wall?
If I just sketch the trajectory, the path, yeah, one can consider that as the time, whatever dimensional time. Then it describes jumping between the two values. That's -1, +1. So it gives a general idea that it's a jump, quantum tunneling, which could be far-fetched analogy. there could be jumps of any kind. But there are more analogies between quantum tunneling and domain wall. Domain wall eventually is a rather very certain configuration solution to this equation, which has certain width. And if we estimate this width, it appears to be just the width corresponding to tunneling process, to typical time of tunneling process. In order to tunnel, a particle would have to go through this potential anyhow, and typical time is this oscillation frequency -1, which is transformed into the length of the to the thickness of this domain wall. And as I said, the Boltzmann weight of domain wall is exactly reproduced by equation for small amplitude.
So, and in terms of the Eisen model, we should regard the epsilon here to compare to the magnetic field and the delta to the temperature, right?
Yes. As you see, it's already some coarse graining of, one can see it as some coarse graining of Eisen model because both variables are already continuous. But well, the physics is the same. There are domains, and one could not make direct correspondence with Eisen model. And why is it so? Because at all costs, imagine time in usual quantum mechanics, so imaginary time are continuous variables. So it cannot be directly mapped onto Eisen model because Eisen model is discrete in space.
Yeah, so you should make it more field theory out of it with London-Ginsburg or something like that.
But it's also kind of, it actually opened the way to solve complex field theory problems. Because again, if you, for instance, consider two-dimensional field theory in 2 dimensions, this is can be presented as statistical, well, classical field, thermodynamics of classical field in 3 dimensions.
All right, thank you. Have a nice day. Bye.
Same to you.
Thanks for the lecture.
Good. Then I finish the lecture and the session.